Okay, today we're going to talk about two topics. I'll start with the modal analysis, and then we'll do the thermal analysis as well. Okay, I already upload this note into Evidence to Learn. Okay, and I'll explain to you what's that note about. Okay, first of all, before we go deep into the modal analysis things, I want to give you a little background of the dynamic of a spring mass system. Okay, what you see here, right here, the first figure, just imagine when you pull the mass to the right, okay, with a force, and all of a sudden you let go that force. What happened to that mass? It's gonna bounce back to its original form. And then it won't stop there because the spring has some elasticity, right? So it bounces back, then it goes right again.
Dạ ông già rồi.
Oh, excuse me, guys. Can you put your mic on mute, please? This lecture is being recorded. Okay, so somehow the force can also defined by the mass times its acceleration. So this term is basically what we had in our first lecture, F equal to kx. But now we just add another term to it. Mass times acceleration is equal to the system. So we manipulate that. So net force is a mass times acceleration, and force being done and stored, all the energy stored in the spring can be defined by kx. And this is the external applied force. So just repeat what I said. When the force let go, the spring will bounce back. Okay. So right here, acceleration is also the second derivative of x. So we write everything in terms of x. And then we put mass over, we divide the whole expression by mass. We get acceleration plus f plus k over m, x equal to f over m. Okay, from the dynamic solution, second order of dynamic solutions, right? This term right here is the natural frequency square. Okay, anyways, this expression and this term equal to this is given. So we just have to remember that and use it. So k over mass is the natural frequency square. Okay, how we develop that is driven by many scientists. Probably a few years of study. We are the lucky ones. We just use it. And always the unit is read over seconds. Okay, now we put everything into matrix terms. Okay, now if you just ignore this part, this is what you learn in week 1, right? Nothing fancy. In this class, we just add one little term right here. Mass times acceleration. Okay. So back to what I said, when the force is let go, the mass just bounces around the spring, and it's called a natural frequency. Okay, it's quite applicable to everywhere. Let's say you play soccer and the soccer ball, bang, just strike on the post of the goalie. okay? And the whole system shakes a bit. That's natural frequency. But of course, after a while, the thing would damp and the shaking, the vibration just stop. But in this case, we assume no damping. So stiffness times displacement factor plus the mass matrix times the acceleration is 0 in this case. So what is the best way to simulate something that vibrates in a constant amplitude? That's a sine function. Okay. Again, this formula is developed by many other scientists, and we are the lucky ones. We just use it. So we use the displacement as a function of time, and u is the maximum amplitude of the movement of the mass. Omega is a natural frequency, and theta is the phase of oscillation. Okay. So if u is sine, first derivative, it turns sine into cosine. And then second derivative, God, it's back to sine again. We love that. So we put everything into the equations in the matrix form. We get this term. And then we isolate sine out of the expression. And we have k minus omega squared times mass matrix times these terms equal to 0. Okay. And we want to put omega in a matrix term as well. So we times that with the identity. Since everything is equal to 0, so we just take that away. And the determinant of this thing is 0. So if we solve for omega squared, we get the natural frequency of the system. I understand, I skip a couple steps right here, okay? But don't you worry, we just have to use this term to get a natural frequency. Now, we know the K of a string matrix, of a beam matrix, of a truss matrix. Okay, we know the identity. Okay, the only new terms we have to deal with in this lecture is the mass matrix. Let's go deeper on this matrix then. Guys, I'm sure you know this term very well. It's in a week 3 lecture, Now let's talk about the mass matrix. Okay, it is defined by the density and then the shape function. Right here, n is the shape function. I know in the previous lecture I used s, but don't worry, the same thing, the shape function of the matrix, of the function. Okay, let's derive the constant mass matrix for bar elements. Remember, we have the shape function defined long time ago, okay? And then we just put that into the matrix form. We take we times that together. N is 1 by 2. When you times them together, it becomes 2 by 2. You take the third integral. Okay, right here, it is a third integral as a volume, but because it's a constant area, so we take the integration one time only. from 0 to L one time. This is the mass matrix for your spring element. Sorry, when I say spring element, it's also the 1 bar element right here. Guess what? I'm a nice guy. Well, at least I try to say that to myself, you know. So I have developed all the constant mass matrix for you already for 1 bar element, beam elements, sorry, and the 2D elements of the 3 nodes. Okay. Now, how do I? Okay, I just show you how I did that, right? How I got this, same thing, same as page 3. Okay, we just get a shape function times them together, take the density, and then the integral. But because it's a constant area, we only take one integral. That applies to 1 beam element's 2 nodes as well. However, for the 2D elements, it's a bit tricky because I don't have a constant area across the length, but it's okay. I did that for you already. Okay, note, please note, there's two columns here. This one is the consistent mass matrix. That one is called a lump mass matrix curve average. Okay, try not to use it because it's not quite realistic. Basically, what it does is I look at that density times area times L. A times L is a volume. Volume times density is what? The total weight of the bar, and then divide by 2. So divide by 2, and then they put it at the end of the node. Okay, 1, 1. So basically, they trying to simulate the whole mass of a bar, and then divide by 2, and put it at the end of the node only, and assume it this way. Well, you may do that if your system have a very fine element system. Okay, but seriously, it's not quite realistic. I prefer the consistent mass matrix method. So if there's a question in the test, you know, try use the consistent mass matrix, you know, and this is not preferred. Okay, but I want to show you anyways because it's in the textbook, and it's my job to show you this. Guys, any questions so far? Did you send me any chat? Let me see. Okay.
What does it mean by consistent area? What? And can you explain more about that?
Consistent mass matrix. Basically, which means I have to do an integration from one node to another node to get the mass matrix of the system. The lump mass matrix, right here, lump mass matrix, I'm not doing any integrations. I just take the mass, divide by 2, okay, the mass of the elements, and divide by 2 and put it in 2 nodes. Okay, that's it. So consistent mass matrix, there's more integrations within, so it's nicely defined within each increment from 0 to L. Let's say 0 to L is 10. 0 to L is 10. So I still have some, if I sub that equations into this mass matrix, I still have some weight. Let's say, okay, from 0 to L is 0 to 10. I still have some weight in a I still have some weight in between. But for the lump mass matrix, right, I have no weight in between. I only have half the weight in a 0 and half the weight when at the end of the beam. Can you imagine that? You know,
I see. I understand.
did I explain that good? Yeah.
Yeah.
So okay, to be exact, like constant mass matrix is more realistic. Lump mass matrix is just an assumption. You know, all the weights go to both ends. You know, well, if you need a quick analysis, yeah, you can do it. But seriously, constant mass matrix is more realistic. Okay, now we define all these things. Okay, let's see how we use them. Okay, example. We have a system. We have a bar element. Okay, and then we need to know the natural frequency of that using the constant mass matrix and lump mass matrix. You know what? Let's cancel this. I'm not gonna ask you to do lump mass matrix because one mass matrix is good enough. You don't need to do two. Okay. Okay. Now, before we let's see. Okay. Always, you know, you have a questions and you respond with a figure which is more comfy to yourself. You know, how you define that, how you simulate that. And check this out. The first term is not strained at all. You know, we've done that many times. Okay. K is AE over L, and then 1, 1, negative 1, negative 1. Okay. The only new thing that we learned right here is the mass matrix right here. Okay. And then we just use that equation from up there. Like page 4, right? Yeah. Density times area times L over 6. Oops. We just use the same thing. We just use the same thing right here. Okay, now we apply the boundary conditions for U1. U1 is stuck to the wall, right? We love it. So U1 is 0. Wow, when something's 0, there's no speed, no acceleration as well, right? So both is 0. Gone. Boom. You do the multiplications. And then remember the term before x, before the displacement, is the omega square. Okay, and that's easy. You know, you just take the square root of that thing. That's your omega. Okay, lump mass. Okay, sorry, internet problem. No, I'm back. Can you hear me good?
Yeah.
Okay, I'm sorry. Let's share screen again. Okay, let's back to my OneNote. So we just finished the first example. Okay. Okay, we just finished the first example. Now let's take a look at the second one.
Wait, Chris, can you actually go back? Like, it cut like halfway through.
Where did I stop?
Well, I think we lost audio around like after the second line after CMM.
Second line of CMM is right here, right?
Yeah.
Okay. The first term, no string at all. You know, we learned that long time ago. It's not strange to you. This is a new term, mass matrix. Okay, and when we just use that from the previous page, you know, we just apply the same equations, and then now we apply the boundary conditions. U1 is fixed to the wall, so of course U1 is 0. When someone is stuck to the wall, there's no velocity and also no acceleration. So U to the second derivative is also 0. You multiply the matrix, okay, and you get U2 accelerations plus this, and then U2 times the AE over L equals 0. Then you put that into this format, okay, always acceleration with no no multiplier, okay? And then you leave x alone equal to 0, and that term will be your omega square. And then you take the square roots of that. This is the natural frequency of the system. Okay, this is the application when there's only one element, right? Let's take a look. What do we do when we have two elements in the same? Because in the question it said use one element to simulate this. Okay, we've done that. Now let's see how we simulate that with the two elements. Okay, nothing fancy. No, we define the local matrix. Okay, right here you don't really have to write it twice. Okay, you can just say K1 equal to K2 equal to this mass. These things right here, same thing. Okay, same here, M1 equal to M2 equal to this. Okay, this is the goal. Always you start with this formula when you assume there's no external force. We pull something and let go, boom, let it bounce around in its natural frequency, natural mode. Okay. I hope by now you understand this term. Very easy. You just put two matrices together. Now, similar, nothing, don't let it scare you, okay? You just do this and assemble your global matrix, okay? You put this term in right here, and then you put another term right here. That's it. Now that's your global system. You apply the boundary conditions, okay? U1 acceleration equals 0, and you get this. Now it's a bit tricky because it's a 2x2 matrix now, not as good as what we had before. What we had before is only one term, right? 1x1 matrix, okay? Now it's a 2x2 matrix. So you have to do more calculations, okay? So it will be, you have to divide K by mass, okay? And then so you have to take the determinants of the expression. Okay, so this term is your, let's see. Okay, first of all, I have to take the inverse of the mass matrix. We have the mass matrix right here. We take the inverse of that. Okay, the multiplier inverse of that is very easy. You just put it upside down. That thing, you have to take the inverse of that. Okay, there is standard formula online, you know, or you can use the row reduction method to inverse that, or you can use Excel to inverse that. I'm totally fine with this. Okay. This formula is from online. You know, I use the 1 over determinants of the original matrix, and then you just flip that side, and you flip that side, and then you put negative on these two terms, and you get the inverse. This. We have the K right here, and then we let this term, you call it UFA, okay? I let this component to the omega square just easier for me to calculate. Okay, instead of writing the whole, okay, previously, instead of writing that thing like 4 or 5 times, I just assume that with a regular symbol. To determine that, I solve for lambda, okay, and it's the quadratic equations. I get, look at that, I get 2 values of natural frequency. So what it means is that when I resolve that system with one element only, I only get one form of how it shakes. But now I have two elements. So I have two natural frequencies. So it may shake in two different ways. That makes sense because we're adding one more note into the system. So one more note, more information between the elements, between the system. So it has more freedom to move around. So it has two way to vibrate. So any questions so far? From page 6, the bottom of page 6 to the top part of page 7 is pure geometry and pure algebra. Nothing fancy. Okay, enough of our bar elements. Let's take a look at some beam elements. Oh, by the way, that's an example of the lump mass matrix for the bar element. You can study it, review it, but you know what? I don't really care, because we already solved the problem by CMM. We don't need a lump mass matrix. Consistent mass matrix is good enough. Okay, let's do another example with a beam element. Same here, both sides fixed, okay? And the beam elements can go up and down, and each node can turn as well. Each node can go up and down, and nodes can turn, okay? These things, you can review your notes in beam elements. I just copy that. I just use that, the stiffness matrix of both beam elements, and I leave it here. This is a new thing that we learned today. Again, the formulas from page 3, I guess. Oh, page 4. That's right. I'm using this term, and I just copy it over to page 9. Okay, and you assemble two elements together. Let's see. This portion is the first element, and this portion is the second element. You should know this very well by now. Okay, and this is the first portion of the mass matrix, and that's the second portion of the mass matrix. Look at that. I love zeros, because you're locking both sides. Okay, you're locking both sides, right here and right here. So anything related to V1 and phi1 and V3 and phi3 is all zero. When the displacement is zero, the acceleration is also zero. What a beauty. Okay, and then you just multiply that thing to the big matrix. So we shrink the 6 by 6 matrix to voila, 2 by 2 only. So we determine the natural frequency by the determinant equations. Okay, same as what we had. We need to take the inverse of the mass matrix. So inverse of the mass matrix is right here. Oh, sorry, this part, and inverse. No inverse. The regular stiffness matrix is right here. That's a regular stiffness matrix. I take the inverse of that thing based on the inverse equation, and then we multiply that whole thing. Again, we let lambda equal to omega square. And we let this term, the alpha, okay, we times this together, and we solve for lambda. And we get this again. Right here, we have two natural frequency forms. Any questions? Okay, if that's the case, read the notes one more time, make yourself comfortable. Let's take a short break, and then we'll come back again at how about 10 after 10? That's right. Let's take 10 minutes break. Drink some water, okay? And I will see you very soon, okay? I won't stop the meeting, okay? But see you soon.